Welcome to all of you in Sankalp Education Pratham classes. I am Sachin Patel, delivered lecture series on mechanical properties of fluids, and right now we are going with the pressure due to liquid column. Pressure due to liquid column. For this purpose, first of all, we have to take the vessel, and inside this we will take the fluid, that is water, and it is filled with water. Inside this we will take an imaginary cylinder with a cross-sectional area is A and height h of that one, and rho is the density of fluid, that means the water is here, and let us consider rho be the density of that water. And right now we have to consider, let liquid column exert force F is equal to mg is here. F is equal to mg is here, where m is the mass of that liquid column, and here to consider here is let liquid column exert force is equal to F is equal to mg is there, and this weight is acting on the bottom of that cylinder. That means the weight of that cylinder is acting on that bottom surface, That means this weight acting on bottom surface having area A is there. That means the force or the weight of that liquid column is acting on that area. Then according to pressure, definition of pressure is equal to force divided by area. Force exerted per unit area is there, and force is nothing but mg divided by A is here. But right now we know that the density is nothing but a mass divided by volume is there, and density it is equal to rho is nothing but a mass divided by volume. M be the small m be the mass of that liquid column, and volume of that cylinder is nothing but a into h is there, and it implies that m is equal to rho is there, and this value is putting inside the equation. You will get the consideration of P is equal to rho into G divided by A, and A is cancelled to each other, and pressure is equal to H rho G is there, and therefore this is the equation of pressure which is exerted by the liquid column on the bottom of cylinder. This liquid column exert the pressure on that bottom of cylinder, and therefore pressure P due to liquid of density rho is at depth h, as thus you can say that pressure P due to liquid of density rho, of density rho at rest and at depth h is h rho g, and therefore the pressure exerted it is does not depends on the imaginary cylinders or area of imaginary cylinder. That is, it is not depends on surface area of cylinder, and therefore you can say that the pressure exerted by the cylinder, it is depends on the height below the surface area, the point below the surface area of liquid. This is the surface area of liquid, and below this surface area. The point is how many distance below that liquid surface, then you will get the pressure is large. When point is just below the liquid surface, at that time pressure is small, because the liquid column above that surface, above that point is very small, and therefore it exerts a very small force on that surface area on that point. When similarly at the surface of sea level, the pressure of water is very low, but when we are moving down and down inside the liquid of sea water, at that time liquid column above you or above the point of your object is increases, and weight of that column is increases. Due to that increase in a weight of column, pressure exerted by the liquid column above that point is exerted increases, and therefore the pressure exerted on any point is not depends on imaginary area around it. It depends on the height below the liquid surface, below the liquid surface, and therefore pressure does not depends on the imaginary surface area of a cylinder, and it is independent on the shape and size of a container. It is independent dependent on size and shape of container. Also P is equal to H rho G is true for both liquid and gas also. This is your consideration of pressure due to liquid column, because the liquid column is here considered here, and this liquid column below the surface of liquid, and at that time the pressure is depends on the height of or depth of the point where we want to find out the pressure below it. Now we are moving with the atmospheric pressure, and we know that the Earth's atmosphere is made up of a fluid. Earth's atmosphere made up of fluid, that is air is air. Air is a combination of different gases, that means nitrogen, oxygen, carbon dioxide, neon, xenon, different gases which is present inside the fluid. We know that about the concentration of nitrogen is 78% inside the atmosphere. Oxygen is 21%. These two fluids or these two air gases are present about 99%. 0.03% of carbon dioxide, and which having the different percentage with different respiration and photosynthesis, different things is there. And this Earth's atmosphere made up of a fluid, and it exert a downward force due to weight, and this air exert downward force due to its weight. That means weight of that fluid, weight of that air exert the pressure and exert the force, and this force per unit area, and this force, the pressure due to that force, that means the pressure due to that force which is exerted by the air or fluid in Earth atmosphere is called atmospheric pressure. atmospheric pressure is there. Atmospheric pressure, and this pressure is nothing. This pressure at any point is nothing but a weight of the air column, which is a unit across a section. Thus, we can say that at any point the atmospheric pressure at any point atmospheric pressure is weight of air column of unit cross sectional area, which is starting from that point and it is moving towards the moving up to the height of that atmosphere, and top of the atmosphere it is a cross sectional area extend up to top of atmosphere. What is the top of atmosphere? It is considered at 8 km, beyond 8 km height, negligible concentration of negligible density of air, and therefore density of air decreases from the surface of earth, and you will get the top of the atmosphere is considered as 8 km is there. That means you will consider here is that density of air decreases as height increases. That means that is density is having small value when height is large, and therefore you have to consider beyond 8 km, beyond 8 km density is negligible, and therefore you can consider the pressure of 8 km air column of height. Beyond 8 km density is negligible, and therefore the height of air column considered as 8 km. That means the height of a air column is considered 8 km because up to 8 km there will be a presence of density of air, and there will be a presence of atmospheric air which having some density, and beyond 8 km this density is decreased, and therefore you can consider 8 km height of air column, and you have to consider this 8 km from sea level, and we know that the atmospheric pressure at sea level is called normal atmospheric pressure. Normal atmospheric pressure is there, and this density is decreased, and region, now this is a normal atmospheric pressure, Those are the definitions related to that one. First of all, we have to consider the earth atmosphere made up of the fluids, and those fluids is nothing but air, and the force exerted by that air is nothing but the weight of that air, and the pressure due to that force is nothing but by atmospheric pressure. And if you want to find out the pressure at a particular point, then weight of the air column from that is taken up to the 8 kilometer, because beyond 8 kilometer there is a negligible density of air, and therefore you have to take the height of air column is nothing but 8 kilometer, and a region where gas pressure is less than atmospheric pressure is called vacuum. Is there. And perfect or absolute vacuum is nothing but no matter is there. That means no matter means no atom or molecule present at that position, and this is nothing but the gas pressure is considered very small than atmospheric pressure, where this region is called as a vacuum. And vacuum is nothing but absolute or perfect vacuum is nothing but no matter present at that point, and this is related to atmospheric pressure. If you like that video, please subscribe my channel and click on bell icon to get the next notification related to lecture series of mechanical properties of fluids. Thank you.